Well, dear students, in this chapter we have, gone through various behavior of, different behavior of gases, particularly perfect gas or ideal gas behavior. And now in this lecture, my focus is how to explain the behavior of real gases. Is this PV is equal to nRT is applicable or not applicable to explain the behavior of real gases? So before going into the detail, first we just take a look for this equation of state, which is used to explain the behavior of perfect gas or ideal gas. So from the equation of state, as all we are knowing that this is PV is equal to nRT. All of you are knowing that if any gas obeys this equation of state, then its behavior is ideal, right? So this equation is simply a mathematical relation between pressure, temperature, chemical amount, and volume. So this is called equation of state. Equation of state. So this is just a little bit revision. Then you will understood how to real gases behaves. So if any gas obeys this equation of state, then the behavior of the gas is ideal, right? And one more point here I would like to add, that if any gas obeys this equation of state under the wide range of temperature and pressure, in the given situation, if this equation is applicable, the behavior of the gas is ideal, right? But if under wide range of temperature and pressure any gas obey this equation of state, then definitely that gas is, the behavior of that gas is ideal. So this is the fundamental equation, PV is equal to nRT. This is one way to explain the behavior of perfect gas or ideal gas, right? Other ways are also indicators, other indicators also we have. Suppose that examiner will not give you this condition, that gas is not this condition is not given in the option, some of the option, some other condition is given. So we have some more indicators, and if those indicators are fulfilled by any gas, then the behavior of the gas is ideal. Okay, so this is the first indication, that if any gas obeys this equation of state in a particular situation or in the wide range, so if in a particular situation, then in that particular situation the behavior of the gas is ideal. And if under wide range of temperature and pressure, then the behavior of the gas is ideal. Second indicator is for ideal gases, for ideal behavior, for ideal behavior, ideal behavior, the mean free path of a gas is much larger than this diameter of the gas molecule. If this situation is there anywhere, then the behavior of the gas is ideal. This is also one indicator, right? Another indicator is for ideal behavior. This is first indicator, this is second indicator, you can say. This is first indicator. So I would change little bit. For ideal behavior, the first indicator is gas must obey PV is equal to nRT, equation of state. Equation of state. Right. Second indicator is for ideal behavior. Lambda is much larger than D. All of you are knowing what is lambda? Mean free path. Lambda is mean free path. Free path. And D is collision diameter. Third indicator is if the behavior of the gas is ideal, then the gas molecule possesses only kinetic energy. Right? So gas molecules possess only kinetic energy. Means in the total energy, the contribution, if only kinetic energy contributes, then the behavior of the gas is ideal. So these are the different parameters. Means for ideally behave gases, that is total energy is of any system is ideally equal to the kinetic energy plus potential energy. If both are contributing, then the behavior of the gas is real. Right? And if only kinetic energy, potential energy if zero, then the behavior of the gas is ideal. So this is also behavior, right? So this is also one indicator through which we can explain the nature of the gas, whether the behavior of the gas is ideal or real. So these are the different indicators uh, which can be used to explain the behavior or ideal behavior of the gas, right? Gases are gases. It's their behavior, whether it is ideal or real. So you can say that real gases obeys the equation of state only at low densities. Means under the very low pressure condition, this equation you can use for real gases, right? So because under this situation the behavior of the gas is ideal, right? So this is the these are the indicators for ideal behavior. Now see what are how to interpret or how to explain the whether the behavior of the gas is not ideal. See, if any gas not obeys this equation of state, then the behavior of the gas is what? Not ideal. Means the behavior of the gas is real. So these are the indicators for ideal behavior. For non-ideal behavior or for real gases, for real gases, real gases or real behavior, real gases or real behavior of gas, behavior of gas this you can write PV is not equal to nRT, right? For real behavior. Means gas will not obey this equation of state. PV means the product of P and V is not equal to product of N, R and T. Second point, PV is equal to constant, PV is equal to K. This is all of you are knowing that if N and T constant, N and T constant, so PV is equal to K constant. This is Boyle's law. So Boyle's law no longer satisfied, no longer satisfied at high pressure. High pressure, right? Means at high pressure, real gases or non-ideally behaved gases, they do not obey this Boyle's law. But at low pressure, they obey this Boyle's law. But only Boyle's law is not mandatory to obey this equation of state, right? Third point is that V is directly proportional to T at constant P and N. You know, this is Charles law. And Charles law, you can say this is breakdown at low temperature. At low temperature, right? Means Charles law is not applicable, right, at low temperature. Similarly, one more point we can add here. V is directly proportional to N. This is at constant T and P, and all of you are knowing this. This is called Avogadro's law. And does not hold strictly. This does not hold strictly at moderate pressure, at moderate to high pressure, at moderate pressure. See, at moderate pressure, Avogadro's law is not applicable. At high pressure, Boyle's law is not applicable. At low temperature, Charles law is not applicable. So if all these laws are not applicable, so PV is equal to nRT, this is also not applicable under high pressure condition or low temperature condition or at moderate pressure condition. So if you want to explain the behavior of real gas only in terms of PV is equal to nRT, then you have to balance all these variables. Means consider this high pressure condition and this low temperature. So if you take sufficiently low pressure, means low density situation, sufficiently low pressure and sufficiently high temperature, then all these variables, all these constraints can be removed and this PV is equal to nRT is applicable. So if a question is asked that this PV is equal to nRT is applicable over real gas or not, so your answer should be not straightforward yes or no. First you have to ask what is the situation. What is the condition of temperature and pressure? If pressure is sufficiently low and temperature is sufficiently high, then this equation can hold and can be used for real gas, right? Basically, now the gas is not real. Now the gas is gas, is still gas. Now the behavior of the gas becomes ideal. So why not? We cannot. Why we cannot use this equation of state? So under high temperature, under we can put a note here. Under high temperature, under high temperature and low pressure conditions, right? A low pressure condition or a low density, you can say. The behavior, the behavior of gas changes from real to ideal, real to ideal. Thus, we can use PV is equal to nRT. So, if the question is asked that can we use this equation of state to explain or to calculate some property of real gas? So don't give the answer straightforward yes or no. You have to analyze situation. So you should ask under what condition. So if temperature is high, pressure is low, so you can use this equation of state to explain or to calculate certain parameters of real gases as well, right? But you know what I have clearly here written. Now the behavior of the gas is not real. Under these circumstances, the behavior of gas changes from real to ideal. So you can use this equation of state, right? Now see, if you see the plot between P and V, P and V, see at constant N and T. So this is a, I mean, you can say boils. plot between pressure and volume. So see this, two plots I have shown here. This is for a real gas and this is for ideal. This is for ideal. See, there is a point and intersecting this and behavior is changing, see, and after that and finally they will coming close to each other, and if you see very low pressure condition, both were merged together again. So at any moment of time, suppose that pressure is not sufficiently low, and suppose that if we take this situation, if we take what same volume, same temperature, and N and T are constant for both the gases. If we do draw a perpendicular from here, so we will get like this. So if we join this point here like this, so this is for ideal gas. So the pressure of ideal gas at this point, see, pressure of ideal gas at this constant situation, constant volume, constant number of moles and temperature, the pressure of ideal gas here is less than what real gas at the same volume, if you have the same volume. And similarly, if you take the same pressure, then the volume of real gas is more, right? Real gas is more. As you move here under low pressure condition after this intersection, so you will find that the pressure of ideal gas is more than the pressure of what real gas. So see here the behavior is changing at this after, before and after this point. So this is a very important graph. You can say when pressure of ideal gas, is more than the pressure of real gas. Real gas. When see, pressure of real gas here in this situation, what I have selected here. So here the pressure of real gas is more than the pressure of what ideal gas, right? And after this point, if you see, the pressure of ideal gas is more than the pressure of what real gas. So under low pressure condition, we can say the pressure of ideal gas is more the pressure of real gas. But under high pressure condition or low volume condition, when volume is sufficiently low, so you can see that the pressure of real gas is more than pressure of ideal gas. So what you can conclude from here regarding the intermolecular forces, because you know all the main cause of deviation from ideal behavior is the intermolecular force. Now can you tell me something that in which case what is happening in this case, in this situation, what I have selected on this graph, when the pressure of real gas is more, means in this situation force of repulsion is dominant between the gas molecule. Which force? Force of repulsion. Repulsion is dominant. Right? And after this point, the force of what attraction is dominant, right? force of attraction. So when you take any point here, so at this point the pressure of ideal gas is more than the pressure of real gas at this point, at this particular volume, right? So in this situation, the force of attraction is dominant. Force of attraction is dominant. Dominant between the gas molecules. P ideal is the basically reference, right? This is the reference, and we are explaining the behavior of real gas with respect to the ideal. So this conclusion you can draw. Suppose that it is asked, okay, the pressure of ideal gas is always greater than the pressure of real gas. You cannot say like that. There is a situation, there is a condition when the pressure of ideal gas is more and when the pressure of real gas is more, right? So this is V dash and this is V. So temperature also play important role here. So many factors are there. So this is one of the representation. Similarly, if we draw another plot, PV versus P. So PV versus P, if this plot is there, then this is ideal. And any deviation from this line, any deviation from this line represents the real behavior. Like if this is like this, if this is like this, right? So these are real behavior. So see, this is what Boyle's plot. Again, PV versus P. PV is equal to what? Uh, PV is equal to constant. So if you draw the PV versus P or PV versus V, so you will get this ideal straight line parallel to x-axis, and any deviation from here, this line, that will represent the real behavior. So in this way you can identify the real behavior of the gas, right? Now see, again I am putting one note here that note at atmospheric pressure, at atmospheric pressure, at atmospheric pressure, PV is equal to nRT is good and well satisfied, is good and well satisfied for most gases, for most gases except vapors like water vapor. So at atmospheric pressure and uh, temperature above than room temperature, or we can say mm, 300 Kelvin or more, 300 Kelvin or more, right? 300 Kelvin or more. This PV is equal to nRT. So what I am trying to say that under normal condition, what we are here under one atmospheric pressure condition, under this normal condition, and sufficiently high temperature that I have written here 300 Kelvin or more, most of the gases will satisfy this equation of state. But except vapors like water vapor. What is difference between gas and vapor? See, gas and vapor, as the name itself indicates here, vapors means the matter is normally in the liquid state or solid state, and by providing some heat we are converting this into the gaseous state. So if any matter normally exists in gaseous phase under normal condition, then that is called gas. And if any matter normally exists in the solid and liquid, but on providing some heat it is converted into gaseous phase, then it is called vapor, right? So this is the difference between gas and vapor. Vapors can be easily liquefied, but gas cannot be easily liquefied, right? So this is the, I mean, general introduction about real versus ideal. What are the indicators, and what are the different violations which can be used to differentiate between real and ideal. So now hopefully all of you are clear that what indicators, what points you can use to differentiate between ideal behavior and real behavior. Right now, let's start behavior of explanation of the behavior of real gases. Now we are taking the gas in that situation when this PV is equal to nRT is not applicable. So what is the cause of deviation from ideal behavior? So first we will see cause of deviation, right? Cause of deviation. So two main cause of deviation. First is the first point, what we have assumed in kinetic theory of gases, that gas molecules are always in ceaseless and random motion. So that ceaseless point is here not applicable. Means we have considered there is no interaction between gas molecule, but here some interaction under certain situation. So first cause of deviation is the interaction between gas molecules. Interaction includes both attraction and repulsion, right? So interaction, this includes both attraction and repulsion. So first cause is the cause of deviation from ideal behavior is this, and second is the finite volume of gas molecule. What we have assumed that the single gas molecule is volume of a single gas molecule is negligible compared to the volume of container, but here we should consider some finite volume, but not always. So finite volume of gas molecules. means when lambda is close to D, right? But this situation will not arise always. This situation will not arise always. This situation will not arise always. Means when this situation arises and significant, then the gas will deviate from the ideal behavior, and the extent of deviation that depends on the magnitude of this attraction, repulsion, or this lambda and D, means finite volume of the gas molecule. So these two are the main cause of deviation of behavior from ideality, right? And this can be explained. So the behavior of real gases can be explained in the following terms. First is compressibility factor. Compressibility factor. Factor Z. Second is van der Waals equation. And third one is virial gas equation. So I will discuss all these three, points are three different terms: compressibility factor, van der Waals equation, virial gas equation, to explain the different behavior and different properties of real gases, right? Now we can see this each term. First, I am taking this compressibility factor. See, compressibility factor Z, right? See, Z is defined as Z is equal to, we can write PV, real by PV ideal, right? So what we can write, this is basically a ratio, this is a factor, basically dimensionless factor, has no dimension. So pressure into volume, this is, you can say, energy, right? So energy of real to the energy of ideal, ratio, basically this is the ratio. So we can write here PV real by PV ideal, we can write nRT. So here we can write V by N. V by N is the molar volume. So PVM by RT. RT. Vm. So Vm is here. Vm is equal to, you can write V bar. This is also one way to write the molar volume, and this is equal to V by N, and this is equal to what? Molar volume. Means volume of 1 mole of the gas. So P by RT, here we can again use here this is the molar volume of the real gas, Vm real, right? Or we can write here PV bar real by RT. So we can write here this is equal to V bar real by V bar ideal for 1 mole, V bar ideal. So sometimes you may get this relation. So basically we generally define that Z is molar volume of real gas, means volume occupied by 1 mole of the gas, and V bar ideal, and given temperature and pressure. So what does it means? See, V bar real is the actual volume occupied by the gas, and V bar ideal is the volume to be occupied by the gas, right? So here we can write here V bar real is the actual volume occupied by the gas molecules, right? And V bar ideal is the volume to be occupied by the gas volume or molar volume to be occupied by the gas molecules, right? So this is the meaning at constant T and P, at constant T and P. Now see, if Z is equal to 1, so you can write that V bar real is equal to V bar ideal. So you can say the compressibility for this gas is normal. Compressibility is normal. And what other interpretation for this? The other interpretation is no interaction between gas molecule, no interaction between gas molecules, right? And what other inference we can draw from here? That molar volume at STP is equal to 22.4 liters. So if Z is equal to 1, means volume to be occupied and actual volume occupied, both are same. Compressibility normal, whatsoever the compressibility to be for a gas, that is there. No interaction between the gas molecules, that is potential energy is equal to 0. Potential energy is equal to 0, and volume at STP is 22.4 liter. Molar volume means volume of 1 mole at STP is 22.4 liter. So this is the Z is equal to 1. If Z is less than 1, if Z is less than 1, so what we can say that V real is less than V ideal. First, V real is less than V ideal, right? Then what you can say, compressibility. What about compressibility? So if Z is less than 1, so compressibility is relatively easy. Such type of situation or such type of gases for which Z is less than 1, or for a gas in this situation when Z is less than 1, it is easy to compress any gas. So compressibility is easy. Compressibility is easy. Which type of force will dominate in this case? Force of attraction, because this volume is less. So this you can imagine, if molecules are attracting to each other, so they will confine into the less volume. So V real is more than V ideal, means you can say that the force of attraction are dominant. Force of attraction are dominant. Dominant. And you can say potential energy is not equal to 0, means some potential energy is there. Okay, force of attraction is dominant in this situation, right? Third, if you take volume, molar volume at STP, so this will definitely less than 22.4 liter. 22.4 liter, right? See, the third case, when Z is greater than 1, then V bar real is more than V bar ideal. Ideal. Compressibility this time difficult. Compressibility difficult. Difficult. And this time force of repulsion, means molecules are repelling to each other, so they will occupy more volume. So force of repulsion is dominant. Force of repulsion is dominant, and potential energy is not equal to 0, right? And volume at STP is more than 22.4 liters. So this time the behavior is what? This time the behavior of the gas is real. This time the behavior of the gas is real, but when Z is equal to 1, then the behavior of the gas is ideal, right? So see, if you see here, uh, if Z is equal to 1, so the behavior of the gas is what? Ideal, right? So, and now we can see different plots of Z versus P. We can see here different plots. See this graph. This is PV bar by RT. So this you can write this is equal to Z. Z is equal to PV bar by RT. See, PV bar by RT. This is equal to Z versus P. Versus P. See, this is the Z value. 1 ideal gas. If it is less than 1, so this is real. Nitrogen is also real. Helium is also having a real behavior, but see the pressure 200, 400, 600, 800, 1000. At 1000, see here 600 all have this. So here Z is equal to 1. At this line Z is equal to 1. The compressibility is normal. Here Z is less than 1, and above this line Z is greater than 1. So see the same gas, if you see the methane at very low pressure, it starts from Z is equal to 1. It is not started from here or here. So at extremely low pressure, every gas behaves as a ideal. So first observation of this, plot, first observation we can say at very low pressure, Z is equal to 1 for all gases, right? At very low pressure. Second observation, this region we can use this region from here to here. We can use low pressure, low oblique moderate pressure. So at low or moderate pressure, Z is less than 1, but except hydrogen and helium. If you see hydrogen and helium, see this is here, it is only helium is shown. Hydrogen is also have this always, Z is either 1 or greater than 1, not less than 1. So hydrogen and helium, except hydrogen and helium, Z is less than 1 for all the gases. For all gases. Means force of attraction is dominant here. So when force of attraction will dominate, then this graph will go like this for all the gases, right? And third point, third observation, Z is greater than 1 at high pressure for all the gases. Z at high pressure at high pressure Z is greater than 1 for all the gases. Means when Z is greater than 1, force of repulsion dominant. Repulsion dominant. When Z is less than 1, attraction dominant. And when no force of attraction or force of repulsion, right? And we can say that for helium and hydrogen and helium, the special observation for hydrogen and helium, Z is greater than 1 at moderate and high pressure, right? So these are the observations. Different observations for different gases for their behavior. If we see, and this is a very important point, the temperature for this plot is 300 Kelvin, constant temperature, right? One more plot I have for you people, and you can see this plot. This is again see, plotted Z versus P at different temperature for same gas at different temperature. So you can see this at low temperature, 200 Kelvin. At low temperature, the behavior of the gas is, see, this varies like this. At 300 Kelvin, see, the graph is moving like this. At 400 Kelvin, see, this is moving. So if we draw a line corresponding to Z is equal to 1, so this is what? Z is equal to 1, ideal behavior. So you can see this is the 600 Kelvin temperature at which the gas is moving along with this Z is equal to 1 line for a longer time. But after that, when the pressure is sufficiently large, then again this will deviate from ideality. Means only temperature or only pressure, we cannot manage the behavior with the help of only temperature, or we have to adjust temperature and pressure both, then only we can manage the behavior of the gas. So see here, at larger temperature, see, at high temperature you are seeing here that at the same pressure, if you consider, so larger temperature, they have more value of Z. So obviously when temperature large, definitely the force of repulsion is dominant, right? So this is the interpretation of behavior of gas under the different temperature and pressure condition, right? So here T and P for a given gas, same gas, these variations are observed, right? So this is all about this compressibility factor and how the behavior of gas can be explained with the help of compressibility factor Z, right? Now I will take up the next one is van der Waals equation, right? So next is van der Waals equation. Van der Waals equation of state.